Today we're going to be going through 2 lectures and an activity. We're going to be talking a bit about data acquisition and how it's done, as well as a bit about electrical signals and what they look like. And then we're going to have a brief activity on teaching you guys how to use a piece of equipment known as an oscilloscope. Without further ado, let's get into this. So in data acquisition, the first thing you need to know is what a sensor is. A sensor is a device that measures or detects some kind of physical property and records, indicates, or however, in some way responds to this physical property. And it does this, often sensors are also coupled with what is known as a transducer, which changes whatever reaction the sensor has into some kind of electrical signal. Often these two, the sensor and the transducer, are integrated together into a single unit. A good example that you guys have seen already is back with the SCEDARSAT. The thermistor's resistance changed with temperature. And another way you can look at it is it was converting temperature into a resistance value. And so you're able to actually measure what the temperature is based off of what, how that resistance changed over time. Now there's a couple of different physical variables that your sensor could measure. A good example are the 3 that you will be using next semester and some this semester as well, of temperature, pressure, and humidity. Some other ones that we've seen in the past for other ACES experiments, we've seen some sensors measure light intensity, the radioactivity, acceleration, altitude, and even electromagnetic strength. There's all kinds of sensors out there, and these are just a small sample of what kind of physical variables you could expect. There are also 2 kinds of sensors, and it depends entirely on whether it is actively emitting some other signal that it's trying to measure, or if it's just passively reacting to some external stimuli. So a passive sensor is just that. It just passively responds to external stimuli and always outputs some kind of electrical signal. These are your thermistors, these are your thermometers, so on and so forth. An active sensor usually emits some kind of signal. The most common example that I use is sonar, where it emits some kind of radio wave and listens for that echo to come back in order to learn some kind of information about it based off of how that signal changed as it went through a medium. Now, these sensors, as I mentioned earlier, output some kind of electrical signal, or at least that's our goal. There is a couple of different kinds of electrical signals that a sensor can output. You can see voltage, current. You might even see how it changes in frequency or signal duration, or it can change the pulse amplitude and width, or there's a large number of ways that the signal output could be put out. This is often specified in the data sheet. Some sensors will even output a digital signal, which will require additional hardware in order to interpret. The first kind of sensors that I want you guys to be aware of are temperature sensors. You will be using these relatively soon. What we often distribute is a 1N457 silicon diode. Now, this is your basic p-in junction diode, and it actually functions rather well as a temperature sensor. As you can see on the graph to the left here, it actually has a fairly linear relationship between temperature. The breakdown voltage, the voltage going across the diode will vary linearly with temperature. And you can get, and this is about negative 2.1 millivolts per Kelvin. And so you can actually, with this in conjunction with some signal conditioning, that's a word that we'll be getting into a bit later, you can actually measure and record what your temperature is. The second sensor I want you to be aware of are pressure sensors. Often the sensor that we often distribute uses a small little diaphragm within the sensor that the actual pressure of the air around it bends and bows it a little bit and creates small amounts of differences in voltages across two pins. And you can, again, use some signal conditioning that we'll go into a little bit later to measure the pressure. The third is a humidity sensor. Humidity sensors are a bit different. They have a bit of a capacitive film that can, the capacitance changes depending on the amount of humidity. Now, one thing, the one that we send out here is a HIH4000 humidity sensor. You will not be using this sensor this semester. This is for the Megasat. But one thing I do want you guys to be aware of for the future is that this humidity sensor is light sensitive. If you actually have light exposed to it, it will impact your signal and give you wonky readings. Another kind of sensor that you will see in the future, again, we're not going to be using this semester, but we will see it next semester, is an accelerometer and gyroscope. We actually have this little accelerometer here on the board. It's a bit of a complicated device. I highly recommend that if you want to learn a bit more about how it works, you read into the data sheet. But briefly, there is a small conductive mass that spans a couple of beams like a bridge and with a conductive plane underneath. And any acceleration force causes that bridge to bend. And so the capacitance changes, and then you're able to measure a change in voltage and you're able to get an acceleration reading from this. This is particularly for this kind of accelerometer. The gyroscope, a bit more complicated. It uses a Coriolis effect, and it's a bit more complicated than we're expecting you to get to know at this moment. If you're really interested, you can go and look up. You can actually see what you may research right here, vibratory MEMS rate gyroscope, if you want to learn more about how a gyroscope works. So as I mentioned earlier, one of the things that you need in order to really measure anything with a sensor is signal conditioning. So all signal conditioning does is it takes an input signal and outputs another one that your electronic devices can interpret more easily. As you can see, like down here, you can see a really noisy signal right here, and then we have a black box of some kind of signal conditioning. And then once it goes through, you get a nice filtered signal coming out where you have all of that you can easily measure. There are a couple of different kinds of signal conditioning. One of the ways you can do signal conditioning is you can amplify a signal. Now, amplification is often used as a way of increasing the overall power of the electrical signal so that you can actually measure it. Many sensors have too small of have a very small output of electrical signal that comes out of it. And you'll have to have maybe 1 or 2 stages of amplification just so that it meets into a range that you can measure. Sometimes also you have the inverse, where the signal is too strong. And if you put that into your Arduino, it's just going to fry it. And you're not going to be able to use it anymore. So you'll need to attenuate the signal. Now, attenuation is not as often used because attenuation is something that naturally happens to a lot of signals, even across a wire. So if you have let's take, for example, you have a mile-long wire and you're trying to transmit an electric signal across it. You're going to have a lot of attenuation across that mile of wire. You might think that's unrealistic, but they actually do have mile-long wires and stuff like that. Another way you can do signal conditioning is through filtering. oftentimes you will see in a sensor's output that there is a lot of noise in it. And through some combination of resistors, capacitors, and sometimes inductors, you can actually clean up this signal and remove a lot of that noise. Now, this is a bit complicated. It's not too complicated, but there is a whole bunch of design into filtering and how you can actually get noise out of a system. Another thing to keep in mind is the impedance of your sensor. Now, impedance is the overall resistance that a circuit has. You guys have already been exposed to resistance, which is actually just one part of impedance. There's also what's known as imaginary impedance, which is a kind of impedance that you can only see with alternating current AC waveforms. We'll be getting into that a little bit later. But what's important is that your input and output impedance, especially of a circuit, often you want these to match. If there is any kind of mismatch, you will actually get signal degradation in your line, in your signal. Or you'll get like some kind of reflections, or anytime you have that kind of mismatch, you can get all kinds of noise and issues that get integrated into your signal. And so one of the things that you can do is, if you have a known input impedance, you can actually design some kind of filtering network in order to match that impedance to another one, so that you don't get that kind of noise and integration. Now, you're not going to. I don't think you're going to be using much of the impedance matching in this particular course, but it is something for the more advanced electronics if you need it. Another one that is frequently needed, a kind of signal conditioning, is level shifting. Now, this is often done with digital sensors that output some kind of digital signal. The level shift, often you'll see that the digital signal will be 3.3 volts or 5 volts or 10 volts or in some kind of voltage logic. And take, for example, your Arduino Mega. It runs off of 5 volts logic. So if you try to put a 3.3 volt digital device into your Arduino, you're not really utilizing the full range of your ADC, and or your digital pins, and that mismatch means that you won't be able to effectively communicate between your devices. I believe you have, at this point, you guys should have already gone through some digital I/O programming lectures, and all of those things are 5 volt logic. And if you try to use 5 volt logic on a 3.3 volt or a different one, it's just not going to work. Now, another part of signal conditioning is span-in base adjustment. So there is many sensors where will have an offset to their signal. Take, for example, your temperature sensor. You're going to actually see a range between 450 to 800 millivolts. And well, that's not a very large range. And if you just put that into your Arduino, into your analog to digital converter, you're not going to get very much of a response. And it's going to be very difficult to interpret that. So what you often do is you'll build some kind of circuit, and we'll actually be getting into this a little bit more. It's known as an operational amplifier that will adjust that base, reduce it down to 0 so that you don't have to, every time you're going through the data, subtract a set value. And then also increase that span, that range, so that it covers the 0 to 5 volts that the Megasat uses. And so here is just a little graph that you can see. This is your range. And what you can do is if you ever want to get it, you can actually calculate what your gain and your offset that you need in order to transfer this this lower base and this the smaller span into a wider range. And so this graph here is actually how you get the gain and offset if you wanted to change that to a 0 to 3 volt signal. But okay, well, we need something that does this transfer function in order to really utilize our sensor to its full capability. Well, how do we do that? That is our good old friend, the operational amplifier. The operational amplifier is a very powerful little circuit that comes in discrete packages. You guys should, you'll be using quite a number of these over this semester and next semester. But basically what it does, it takes 2 input signals and it outputs 1. Normally, what it will do is if you, without any additional signal conditioning, is if the voltage at pin 3 is higher than pin 2, it'll output the voltage at pin 3 on the output. Vice versa, if input 2 is higher than input 3, it will output the signal at 2. And you'll have some power conditioning, but that is whenever it's being used as a comparator. There is a better use for this, however, that we will see. And another thing, whenever you are looking at an op-amp in a circuit, it's important to know that there is some simplifying assumptions that we make to do the analysis. Now, these are, by definition, assumptions, and they aren't necessarily true. The first assumption is the output attempts to do whatever is necessary to make that voltage difference between both the inputs to be 0. This is often done whenever you have what is known as a feedback loop into the in that circuit, and we'll see that in a moment here. And also that the inputs into the operational amplifier are actually 0. There are no current. Now, in reality, there actually is a very, very small current that goes into the operational amplifier inputs, but it is very small. And for the applications that you guys are going to be using it for, it should not impact your sensors or your signal conditioning. And so, again, a little bit more about operational amplifiers. There are a couple of different packages that have different amounts of operational amplifiers in them. They come in single packages, dual packages, quad packages. I've even seen one with 8 operational amplifiers inside of it. They are a very common device used within signal conditioning and other circuits as well. So the first kind of signal conditioning circuit I want to show you here is a buffer. And this is what as I mentioned earlier, this is what is a feedback loop here. So the output of is connected to the input of 2. And what this does, all it does is it mirrors whatever input Vin is here. This is what is known as a buffer. You use this whenever you need some kind of voltage or current impedance between components. Perhaps your sensor is too sensitive, and if you try to draw current down, it take, for example, you need just to add a little bit of delay into your signal. You can use a buffer, in that case, add a small amount of delay and separate your input from your output. Most of the time, it's used to protect your inputs from your outputs and make sure that there is no feedback going to your sensor. The second signal conditioning circuit is what's known as an inverting amplifier. In this case, in our feedback loop, we have a resistor connected in series with our input. And what this does is it actually multiplies your input voltage by the ratio of your feedback resistor over your resistor that is in series with your input. And you can actually see the equation up here. Now, this is an inverting amplifier. You will see that there is a negative sign here. And that's just has to do with that base assumption that we have from earlier for the circuit analysis, where it will do whatever it can to make sure that this voltage here at 6 is the same as these voltages here. The next signal conditioning circuit is what is known as a non-inverting amplifier. This one, your input goes directly into the operational amplifier, but your feedback loop goes to the this negative terminal over here, and you have a different feedback loop here. And if you do the circuit analysis here, you find that the equation is 1 plus the ratio of the feedback resistor over that input resistor. And this can be useful in a couple of different scenarios, such as adjusting your span of, say, a temperature sensor. The third kind of signal conditioning circuit is what is known as a summing amplifier. Here you have multiple inputs coming into your device, but you only need one output. This is often used for whenever you need to count things. Each of these resistors will have some kind of ratio associated with each other. I personally haven't run into summing amplifiers too much in my work, but it is basically two negative inverting amplifiers put together, and the voltages of each one are multiplied by the ratio of the feedback resistor over the associated input resistor. Oops, sorry, 1 second. There we go. And then the last signal conditioning circuit with operational amplifiers that we want to teach you guys about is what is known as a difference amplifier. In this case, where we were trying to add up two signals, in this case, we want to look at what the difference between two signals are. If you recall back with the pressure sensor, it actually outputs a small signal difference, and then we want to measure that difference. And so we'll use a difference amplifier to measure the difference, to measure that. And in this case, you have you subtract the two input voltages from each other by the ratio of the feedback resistor versus the initial resistor. Now there are some simplifying equations that we do here. We pick our resistors so that this equation ends up being true, because it can be a rather complicated equation if you do the math. And then finally, this is just an overall flow of the data of how everything goes into your megasat ultimately. So we have our sensor, and our transducer, which outputs some kind of electrical signal to our signal conditioning. We convert that signal into some kind of form that our ADC, or our analog to digital converter, can handle. And once we're able to turn it into a digital signal, we're able to collect it, store it, do some kind of analysis to it, and then we can read it out and do whatever kind of analysis we need to do with it.